The 12 rotor is a thing of myth. I've seen gossip such as it's never ran, all the way over to it's made 2,000 horsepower at idle. Well, I will tell you that it is a very real engine, and it has ran. Not only is it the world's only 12 rotor, but it's also one of the very first billet engines. I am honored to make a video with this title. Looking at the things that are wrong with it only exists because of the guy that created the engine, Tyson Garvin, actually showed me most of what he thought was already wrong with his first revision. He made this back in 2008, and back then, he was walking and even running while I still had my shoes tied together. There are so many people that have made it possible for people like me and the internet, YouTube at large, to learn about how to make these engines even better. And I think that's my favorite part. Quit the gatekeeping and share what we can about rotary engines. We are gonna go through the top 10 to 12 things wrong with this engine, and they are actually critical. This isn't just for the title, but also because these are things that we are going to address in both a short-term and long-term solution. This engine was made back in 2008, and a lot has improved in general. A lot of people have learned even more information about how to make a rotary engine run even better. This engine, the core of it being right here, was built as a marine application. And I'll tell you what, number one on most of your lists of what's wrong with the engine, it's rotary, is absolutely wrong. A rotary engine in naturally aspirated form is one of the most stout motors known to man. I'm telling you, 300,000 miles and a rotary does not skip a beat. Anybody that's got one, you don't even hear from them because they're out driving. They're having a fun time. It's only when you turbocharge do you get into problems. The only drawback to using rotary in any application is they generate a lot of heat. Well, it's a marine application. You have a massive ocean of a radiator. So coolant comes in, goes through the motor, and coolant goes out. Essentially, you have all of the ice cold water to cool this motor down. So what you would have thought was number one is not at all. This engine was absolutely perfect for what he was making it for. Where I might think that this isn't a problem, I'm sure a lot of you are gonna say this is the problem right here. 12 rotors, apex seals, haha, jokes all day long. This is actually probably one of the best, safest, most solid parts of the engine because they are Mazda rotors and they've been used in hundreds of thousands, if not millions, of engines. No real guesswork there. The only issue is that the width of these rotors vary. And so one of the very first things that we did was standardized how wide these rotors are so they could be interchanged anywhere in the engine. The very first issue that is actually pretty critical is left, a telltale sign from the engine running back many years ago. These little deposits tell you something very interesting about this design. First of all, is that oil and residue can get in there. That's actually kind of a concern because you would think that this is water cooled when in fact it's not. It's just air pockets behind this surface. And so we have aluminum and then air, and air is more of an insulator than ability to remove heat or move heat. So we now have air pockets hidden underneath here, but that's not as big of a deal as the fact that the intake port right here, where oil and gasoline and air all travel through. They come through on the top, travel through here, and then come out to the rotor here. The problem is there's nothing sealing this from all of this. My biggest concern is that at full tilt, the gasoline is capable of igniting or auto-igniting, I don't know, but say 500, 600 degrees. I know that this combustion chamber gets extremely hot, and with air being the only thing behind this steel, I would be concerned that you could ignite this in there. Now, it'd have to be perfect. It'd have to be a nice vapor. Everything would have to be absolutely critically massed to cause that to explode. Nonetheless, you shouldn't have fuel in a place it shouldn't be. If this area actually got that hot, these O-rings would have long since melted, which actually some of them did. I would like to machine an O-ring specifically right here, and then also I would have loved to have water or coolant or even oil going in these holes somehow. Actually, there's probably a way to do that. The timing of a rotor is dictated by this gear right here. It's called a stationary gear, and the rotor sits on there, and while the E-shaft spins in circles, the rotor dances around this on each gear tooth. Over here is the combustion chamber. So when you explode, for the lack of a better word, when you ignite, there's a desire for everything to push this way. And of course, it doesn't push the gear over, it ends up rotating, and that's where you get rotational energy from ignition. This is that same side, right? And look at how little material is on this side and this side. This was done out of absolute necessity to get the oil to drain to the side here, but That doesn't change the fact that this aluminum is much weaker on the two sides where this gear is actually going to be experiencing most of the force. I don't think that this is going to be a make or break deal, but then that combined with the fact that this top bolt is missing on every single one of these makes it a little bit of a concern. Now, what this bolt is on the back side of these, you can see that that was actually what the traditional motor uses as an alignment piece. So I would actually wish that we could put more bolts in, or we might even drill these out to get that to align. In microscopic levels, you could actually cause this gear to bend this way, and you don't have a bolt fighting it. So all you have is really this here, and it's pivoting off of these four. That's being very pedantic, but in reality, when a bearing is only 0.003 of clearance, that does make a difference. Another thing is that these are fine, but see all these bolts right here? They're perfectly fine for being slightly too short, but again, because of the lack of material, I would like to have them the full depth. I would actually rather have longer bolts cut down. When we compress or pull this material, there's nothing in that hole, so we have even less metal. Even though the bolt is a different material, that bolt helps prevent issues all the way through, so might as well use as much of the length that we've been given. Now here's probably the biggest one that's gonna bite us in the ass. This is no disrespect to the creator of this engine. This was built when I was in diapers, and I was wearing diapers yesterday. The issue is that the oil system is a very big challenge, and I don't even have a better way of doing it. The fact is, it is what it is. You see these little air filter looking things here are basically the dry sump inlets. Oil transmits through this block in multiple spots, which is kind of similar to the stock block. I would love to have these little dowels between these to help prevent the O-ring from busting out, but that's not really my concern. My concern is that the oil is fed through here and goes to this one and then drains down to the bottom. There's a hole right here, and it sucks it out through a vacuum. The problem is that now we have this one being fed here and then drains to this one. This one also fed through the center here and then drains to this one. Now we've got a problem where this one isn't the same as these. It also gets the waste oil from these two. If it was just 1-to-1, that's not a big problem. We have a vacuum here, right? And imagine having two straws and one's in air and one's in your drink. Which straw are you gonna pull the easiest from? It's gonna be the one from air. So you're not actually gonna vacuum up your drink. When one of these channels gets free, that means that it stops producing a vacuum and pulling on the other channel, and so then that just more or less would build up. I think he tried resolving that was by blocking the center one off and adding a little bit of resistance to the upper ones. That's the right approach, and I think that we can make that a little bit better, but that is going to be a problem with oiling as we go on. I would imagine that these rotors would actually be more likely to have oil escape the oil control rings, because if you block this off, I've done this before on my motor, the blow-by can't get away from the combustion out the oil system. So the blow-by actually starts bubbling, essentially pushing out of the oil control rings. This engine was designed basically naturally aspirated. And our problem here is that turbocharging a rotary, this is all aluminum. On traditional engines, it's kind of guided inside of a steel sleeve, and that prevents you from putting a lot of the heat to the outer aluminum. I'm a little concerned that these Corvette or whatever style crush O-ring things are going to be a problem. And I'm also concerned that there's no real way to encapsulate this. If you have 2 square inches and 28 pounds of boost, you're talking about 60 pounds of force trying to pull these two apart. You'd like to have multiple bolt holes to prevent that from occurring. You don't see that here, and you see them kind of on the other plates or in different places, and I can't tap into these spots. All of these coolant holes. The other thing related to the exhaust is, see this one right here, the center exhaust port? That is a different angle, not timing angle. This angles like that, where these are actually flat, perpendicular, like the traditional engines. You have more material here that will absorb more heat. The exhaust coming out of here is a different profile than the exhaust coming out of here. These two are identical. We can treat them as such. Here is something that's a little controversial, and I think it's very exciting, but it's something I do not have experience with. This is one of the E-shaft pieces. The way he did this is beautifully modular, and I checked all the splines, and even though he said he did them on like 1940s equipment, these are really impressively squared up. They're consistent and interchangeable. So very impressed with that. But we have an issue where these bearings have been beaten to shit. And I've got replacement ones. Now this bearing style comes from SKF, so I've ordered the quality 10,000 or 9,000 RPM bearing replacement. This can handle side load, meaning load this way. They're mostly meant for radial load, not axial. That's the correct terms for that. There is nothing holding this E-shaft together this way. You have an E-shaft that will have oil pressure inside of it, and while it's not that big of a deal, the oil pressure is actually causing all the pieces to kind of want to separate. That would technically be one of the things it would naturally do. You have an E-shaft that wants to come apart at some microscopic level, like these pieces right here. This E-shaft has nothing to hold it together other than this bearing here, and then the equivalent bearing on the other side of the motor. So these bearings are very critical to the containment of the rotary engine E-shaft on this motor. It's not so much a problem as much as a concern compared to the traditional motors. There is no end play. You can't test end float. You can't test any of that because that doesn't exist. Now, this one right here is bad. I'm gonna replace all of them just in case. This is one of the most obscure issues with this motor. These gears are all what tie the 3 4-rotors together. And so here is a very weird issue I've noticed while trying to figure out the timing of the motor. Let's just ignore everything else and just look at one of these. This is a 4-rotor, and I know that world pretty well, and so we can say one of these teeth or one of these valleys is top dead center. It's not exactly on a tooth, but it's like right before the side of the tooth right there is 0 degrees on this motor. Nice and straightforward, simple enough. It starts getting interesting because we have 2 different scenarios. We have one where there's a gear between them, and 2 where they're touching each other. All 3 of these gears, I confirmed it with the guy that built it, they're all machined the exact same way. So they all have the same teeth and they all have the same splines, same rotation. This one's not that one, and vice versa. You have a scenario where either way, one of these is off. This is a tooth, it goes between 2 teeth, and this is a tooth that goes between 2 teeth. These 2, in theory, could be at identical top dead center. And so when you spin the whole motor, and this one's at 300 degrees, this one's at 300 degrees. The way that gears work, these 2 gears cannot be in the same tooth spot at the same time because they have to touch each other. So if this one's at a tooth, this one has to be at a valley. If they were in the exact same spot, they would be touching like that. What I need to do is make sure if they're like this, well, there's 60 teeth, 1/2 of a rotation, that's 3 degrees off. So 3 degrees is both a massive number and a very small number at the same time. You want to know how big of a deal that is? Put your engine at your most safest, extreme timing number you want, and then add 3 degrees. You can tell anybody that's a relatively experienced tuner, ooh, that's uncomfortable. If part of the motor is running at 3 degrees off, that means that we don't have an even consistent pulsing. You could engineer it and do that, and I'm not exactly sure how this was built in terms of like timing from here to here. This is the sort of stuff that you have to make sure is exactly the same if you're handed a motor that you didn't build. If 0 is right here on this one, is 0 at the same spot here? I can't tell yet because these can shift a little bit. Thanks to the Haltech, we can do this, is once the engine is all together, say this one is 3 degrees off, that's fine. We can adjust and make all of those 3 degrees off. We come to a very technical issue, as all of these kind of are. It takes a lot of processing power to fire this engine as a 12-rotor. There becomes a couple realistic challenges to that. One is that you need an obnoxiously expensive computer to run this because there is no other engine that runs like this. So there's a shortcut to this motor. There are no counterweights. And I would almost say it's a bad thing. We don't get to run it as a 12-rotor right now. It will fire all 12 rotors. But what you see here is the current solution to this engine. These 2 rotors are firing at the same time. These 2 rotors are firing at the same time. So if you look at just this much, you've got 180 degrees and a rotor is firing no matter what. If you had to splice wires, you could splice wires from this one to this one, spark plug wires, and it would work. Same thing to here. So this is actually running as a 4-rotor, as a 2-rotor, because these are on opposite sides, and you get this kind of lub-dub thing going on. It actually balances out. The thing is, though, is that it's still a 2-rotor, or is it a 4-rotor? You could argue either way, the way it's running, but no one can deny the fact that there are 4 rotors running at once. This gives you the ability to splice wires together, and that's what we're going to do with this 12-rotor, is that a Haltech R5 can run this engine all 6 sets of 2 on one computer. That would require 12 spark plugs for leading and trailing spark outputs, and at least 12 injectors spliced together. A set of primaries, a set of secondaries, a set of primaries, a set of secondaries. If I go to turn this into a traditional 4-rotor, which is where each of these fire at 90 degrees from each other, we need counterweights. We do have this slot here, and we do have these gears here that we can ultimately attach counterweights to, but we don't at this moment. Because of both technical limitations and physical limitations, this will run as a double pulse 6-rotor, which is going to still sound way crazier than a 6-rotor because we have 2 rotors firing at once. This is probably the most expensive gold mine that is only useful for this engine. Originally, when Tyson built this motor, he built the ability to have 2. His boat could take 2 engines. Why not make 2 12-rotors, as if one wasn't crazy enough? These are the steel inserts, faces, and they're beefy. This is only 3 of them. There are a couple that are on the engine right now, or that were delivered with the motor, that were tarnished, scuffed, or whatever the case may be from the engine eating shit for a brief moment. That's why it was brought to us not running. We're going to get accounted for all of the faces that are good or don't need any work or are looking flat, and make sure we have enough accounted for to build the entire motor. The same thing goes for these, which are probably the even more expensive, impressive piece. The fact that each one of these was wire cut out of a block of steel is mind-blowing. Thankfully, we have all of these spares as well. I don't think any of these were damaged. Tyson just sent me the information on making beautiful O-rings ourselves. We have the material, we just need to get the primer and glue. There's a couple O-rings on this thing that are missing. We will make those as well. The prep is so different from any other rotary engine I've ever experienced. We have found a simple but fundamental challenge to the way this engine is designed. This plate is beautiful, thick steel, or some sort of alloy of iron. It's not cast. The thickness helps with it preventing any sort of deformity. The problem is, the only thing pressing really hard from one side is this. And it is pressing on the very tip of this entire piece, steel on steel. On the other side, mostly the pressure is coming from the center of all these O-rings, pushing inward the other way. So what you get is a natural desire for this piece to volcano, to bow inward and collapse on the rotor. Especially as this engine comes up to heat, that aluminum that's all on that face there is expanding more than the steel is, and it is pushing a lot of pressure on this entire plate, but the outside edge is being held by the steel, and so the inside of these plates end up being conical. They cave in. So, how do we know that? Well, check this out. Look at how far that straight edge can teeter-totter. We were originally going to grind this down. Now here's the problem with that. What happens when we grind that down? This section becomes thinner. Thinner center area right here is directly in front of this O-ring. As this gets thinner, it still is going to push it up higher, and now we have the ability for the oil system to escape, collapse into these open pockets and into the intake. We need to keep that center area of metal the same thickness because that's the whole way he designed the O-rings. How are we going to solve that? We got a temporary solution right now. We are just simply going to play devil's advocate, and we are going to take this plate, put it in backwards, evenly on the piece. We happen to have a bearing puller meant to do this job. We know that it's actually expanding on the combustion expansion area, so you can see it's off-centered. I have it down on this side. I get it to snug right there, and we're going to do 3 pumps, and you're going to see something really wild. Same piece, but now look at all the light coming in through the center. It is reversed. Steel has a memory like a spring, springs are made out of steel. We are going to undo the damage that's been done to it by doing the equal and opposite. This one's a little aggressive. I could probably use one more pump.
It's a lot better though.
But it is, yeah, you can already see it is considerably better. So that's what we're going to do to solve that. With all of those problems come all of the short and long-term solutions for each one of them. That said, the whole reason we're doing that is because right now we are in the process of filming the entire assembly and ultimately firing up this motor. None of these problems are actually life-threatening for running it at least once. You can see 12 rotors takes a long time. This is about 3 to 4 days of just prepping rotors, even with having some of the existing ingredients. But that next video is going to be out very soon on assembling and getting this motor ready to